So we move on to the third communication, Capucine, Dupont, this time more oriented towards chemistry and the valorization of value added from the wood. Capucine, can't hear you.
Vous m'entendez maintenant, je pense. J'espère.
C'est tout bon. Yes.
Là, normalement, vous devez voir aussi.
Now you should see my screen as well. You hear me and see my screen? Yes. Yes, we do. Thank you, Hervé, for this kind introduction and for this invitation to this seminar. Indeed, well, good morning. And Hervé, as Hervé said, I will treat another topic about inflow in channel wood and or Instream wood, and I'll talk about Instream wood as a high added value material, in addition to Hervé's first slide, where Instream wood was used as to create a work of art. I will talk about that. And first, to tell you briefly who I come from. I come from Grenoble in the Alps, but for the last 4 years, I've been working in the IHE of Delft Institute in the EU, in between The Hague and Rotterdam. When you say Netherlands water, and institute dedicated to water and the environment, with 3 main missions. First, to teach and train professionals and to do research and then development of sectorial organisms in the development, the competence of a stakeholder or in water, environment, and associated infrastructure, especially with a focus on transition and developing countries, because we are members of the UNESCO. Among the research theme, one dedicated to the valorization of resources, and mainly, well, notably, one dedicated to what they call biochar for various applications. Biochar, what is it? So how do we go from a given resource to biochar? What do we do with it? Well, let me give you one slide of presentation. We'll go from the beginning to the end of the process. So we start from a resource, and resources will be classified in terms of dry resources. They less than 50% of the moisture. There'll be forest wood, possibly, our farming resources like hay or straw, and then there will be wet, moist resources with more than 50% of humidity, wastewater treatment, sludge, or agri-food waste. Dry resource may be converted to pyrolysis by increasing temperature between 300 and 700 degrees, and with no oxygen, in order not to have combustion, and of course at atmospheric pressure. In such conditions, where there will be a release of volatile material, which includes gas, could be carbon monoxide, methane, the condensable, water or organic molecule, we call them the tar, and what is of interest to us, most of the product we call the biochar. Biochar, as you can see, looks like carbon, coal. It's dark, it's a high carbon content, and it's porous. When for the wet, moist or resource or wet resource, more than 50% humidity, we do have a problem with pyrolysis, because we will purely use energy to heat up water, to evaporate water. So it's not all very interesting. And there will be what which is a hydrothermal carbonization. Well, it starts from we hydro, that is, we use water, thermal, we use temperature. What we do, and what I often use as an image to do this, is the steam cooker, where we will put we could put wood, in this case. We mix it with water, possibly, and then, if necessary, we close it, we heat it up. There, in this case, usually 180 or up to 280 degrees. And after that, there will be pressure. Pressure will be generated between 10 and 30 bars. And then there will be the formation of more volatile matter, a bit of gas, mainly CO2, and also liquid, organic matters, inorganic matters, and again, in these conditions, biochar, which we call, because it is hydrothermal conversion, we call it hydrochar. Now, be it pyrolysis or hydrothermal carbonization, I will use the term HTC. Biochar can be will be submitted to a post-treatment to improve its structure, its density. It could be thermal post-treatment, or it could be mechanical post-treatment to improve the density, the pelletization, in order to, based on the applications or the end purpose. Now, don't be misled by the 5 arrows here. There is no, we don't have just 5 applications. Often I use an article which is entitled The 55 Applications of Biochar, and which start by saying, in fact, there are far more than that. But in this case, I've used the first two applications, which are the most mature, and 3 applications where we work as well. So, first one, well, as a fuel, it is a fuel, combustible, to use biochar as a fuel, and this is relevant to replace the wood in the developing countries to avoid deforestation, as well a mature application, which is the enrichment of soils to improve the crop yield, and we also improve the water retention in soils and sequester, and to do carbon trapping or sequestration, and more perspective, the utilization of biochar to filter, to eliminate pollutants from gas or in water, used as an additive in anaerobic digestion. We use biochar as a catalyst. And finally, and this is certainly the most interesting part, a more prospective application, but which is with very high added value, the use of biochar in power storage, energy storage in batteries or piles. So this is the global vision. Now, more specifically, now we look in the batteries to go from floated for Instream wood, floating wood, we do hydrothermal carbonization, HTC, we obtain biochar, we do post-treatment of the biochar, and we use it in sodium-ion batteries. This study was carried out, which is still in progress within the NAIMA European project, together with the support of H2O Lyon, and in collaboration with the CEA for NAIMA. I did not do the work, but even though I'm discussing it today, the work was done, and it is still being done by Abdullah Katarne in a master thesis supervised by myself, Hervé, and Mario Franca, and also a thesis in progress. The Julie Michel, she's also listening, and she's doing a PhD, co-supervised by myself and Loïc. Usually, when I do this presentation, I start by explaining to people what in-channel wood, or considering the participants. I'm sure you're all aware, if not better, you're more knowledgeable than me. So I'll go straight to the point that we know that in-stream wood accumulates in dams and can pose problems to the structure. We see it as a problem waste. We extract it mechanically, and we could say, but it's a little explored resource, a significant quantity grouped in a reservoir, and it's different from other bioresources or other biomasses which are scattered. Here we're lucky because it has been regrouped and collected, and then we've seen it in the previous presentations. It has physical-chemical properties similar to forest wood. No, why should you convert it? Why should you convert it by HTC, by hydrothermal carbonization? Well, first, this is a higher added value product that would be obtained, that is obtained with other processes. Floating wood in Instream wood can be burnt for combustion. There we have a product with a higher added value thanks to this process. And as I was saying, the properties of the wood are a priori suitable for this conversion. Then, in stream wood, if we let him dry, well, it will get closer to a dry biomass, yet it was in water for a long time. So it is very wet, very humid, so moist. So it may justify the hydrothermal carbonization. And other advantage is that it will eliminate part of the inorganic that could be present in wood and could be problem during the application.
Now, the final thing, why take an interest of its use in batteries, and in particular in sodium-ion anode batteries? I'm not exactly how many of there are, but if there are around 30 of us, that makes around, let's say, a minimum 60 lithium batteries if we count mobile phones and laptops. These batteries are very effective, but there's a problem of lithium. The problem with lithium is that it's only available in a few regions of the earth. And when it's extracted, it is highly polluting. So we need to find alternatives. And one alternative could be the sodium-ion battery. Why? Because sodium is available in far more abundance, and as it is more abundant, it's also not very costly. It has also showed excellent electrochemical performances. So to go a little further, I'm going to very simply, let's just have a general overview of the question here. So the principle of a sodium-ion battery. Well, we store energy in the form of redox reactions. In the scope of a sodium-ion battery with a cathode, we have elementary sodium, that's the cathode, that's the positive electrodes. And in the charging phase, we have sodium ions that go through the electrolyte and which join the anode, the negative electrode. Parallel, we have electrons that circulate in an external circuit. So that's during the charging. And we have a reconstitution of elementary sodium in the anode. When the charging is complete, we have the reverse phenomenon that takes place. That's decharging. But what we're more specifically interested in is this anode, because this is made of carbon. I've represented it here with some very organized images of carbon, which are levels of carbon, which are close together. The problem is that that's all very well for lithium, but sodium bonds have trouble adhering to this type of material. So sodium ions manage to slip into material that is more disorganized. We can call this hard carbon. It works well. The sodium ions can slip in and slip out easily. The problem with this material is that it's formed from fossil polymers, so they're not very sustainable, and it's very costly. So what solutions? What are the possible alternatives? Well, this is where biochar comes into it, because this is a case of it's a renewable source. It's not very expensive. And it is a material that is non-graphitizable, so it will naturally remain disorganized. So for the past few years, people have been very interested in this solution for sodium-ion batteries, but there are very few studies carried out on the use of hydrochars. It was more pyrolysis. So if we look at everything I've just presented end to end, this brings us to the objective of the study that was carried out on Instream wood. We wanted to study the feasibility of using this Instream wood converted by hydrothermal carbonization to use it as an anode in sodium-ion batteries. So how do we go about this? First of all, we collected samples of Instream wood in the Janissia dam. We proceeded with its physicochemical characterization. We turned it into hydrochar, and then we tested them in sodium-ion batteries. So the first step, the sample. So once again, I'm sure of you, many of you are very familiar with the Genesea Dam. As we said previously, the wood is extracted mechanically to keep the dam safe. It's stored near the dam. So the idea was to collect samples, more particularly 21 samples were collected by a little over a year ago. And these samples were classified according to the species. So they were classified with the help of the University of Lausanne in collaboration with Virginia. And what we saw in the samples is that we found 4 broadleaf trees. I've kept the Latin names here, Salix and Fraxinus, but we separated the bark for these, and we also had a conifer. So what results, what were the physicochemical results that were interested us for in order to use them? Here for the different samples, you have the ash content compared to the dry mass of the wood, and the content in carbon, hydrogen, oxygen. So the carbon, hydrogen, oxygen contents are similar to those of what I call standard wood, what we call green wood that we find in the forest. And maybe to be discussed with Virginia, I saw that in your presentation, you said that there was maybe some organic decay. But in any case, what we found here is that there did not seem to be any visible organic decay, a loss in one of the majority elements. But maybe that can be discussed later on. And the ash content, I saw that that was mentioned also by Javier. And so indeed, a very low content, similar to standard wood. So we have values around 1%, except in the bark, where we're closer to 10%, which was absolutely expected. However, this was good news because it showed that there was no pollution. We thought there might be external pollution, for example, during the storage after collection, maybe with earth, but apparently this was not the case. And that's very positive for the battery application. Regarding inorganic elements, I mean, the composition of this ash, of this percent or 10% in the case of bark, here you have the different samples. And on the vertical axis, the different elements. So in milligrams per kilogram this time. And what we can observe and what was also expected is that we mainly have calcium in all of the samples, similar to greenwood, significant content in potassium and magnesium, and quite significant content in silicium in certain samples. Maybe a little bit of earth, therefore, but very minute quantities and lower than values that have already been noted as problematic in the scope of sodium batteries. So once we characterize the samples, we wanted to convert them by hydrothermal carbonization. So we did this in the lab in the IHU. Here you can see the experiment. So we have the thermal reactor. We put 6 samples through it with duplicates, and each time we mixed wood and water in the conditions that you see on the top right box, and then we closed the reactor. And it was a 2-liter reactor. We brought it up to 200 degrees and we left it for 12 hours. Once it had cooled, we separated the solid and liquid phases. We dried the hydrochar that is obtained, the solid part, for later characterization. So a couple of words on the results obtained, in particular the mass yield. So how much hydrochar did we obtain after HTC? If we look at the initial dry wood, it's about 65%, and that is typically what is expected for this type of material, and it's a similar yield for all species. I won't say more on that, but what I do want to say, maybe talk about the properties of this hydrochar. So what's interesting, it's a very big table, but it's interesting to compare for each sample the raw wood with the hydrochar. If we look at do it for the first line and the carbon, we can see what we observe in all of the samples. The carbon increases. Hydrogen and oxygen, we can see that they decline each time. And once again, these are trends which are compliant with the literature due to the different chemical reactions that take place during carbonization. What is interesting to note, and this was not necessarily expected, but it depends, is that the ash decreases in all samples, as you can see here. So this is interesting because ash is not a very good thing if we want to create batteries. So, but if we look for bark, things are quite stable, or there's even a slight increase. So we can observe the fact that bark has always been a particular case in all of the trials. Now let's look at the final step, the post-processing of the biochar and testing in batteries. So to improve the structure of the hydrochar and to make it very similar to hard carbon, we have to undertake a pyrolysis, a post-thermal treatment, to which it's taken up to 1,400 degrees in an inert atmosphere, and we leave it for 1 hour. This will essentially modify the structure. We will lose matter as well. And to give you an idea of the yields, here we have the hard carbon yield that we obtain if we look at the dry percentage of wood. So basically we obtain about 20 to 25% of hard carbon when we use dry wood initially, and this whichever the varieties. And this is quite similar with what we find with other biomasses when we turn them into hard carbon. It's slightly higher for bark. Once again, it's a particular case related to the higher content in inorganic elements. This is hard carbon. The idea is to use it in the battery. So what we did is a test in the lab to characterize the electrochemical performances. We therefore mix this. I left the English term, the slurry, with other components. And this slurry formed the carbon electrode, which itself is assembled with other elements to form what we call a coin battery. And this is what we will test, a coin cell. And this is what we test. We test it with a galvanostatic test. Once again, not going to go into the details of what a galvanostatic test is, but I will just explain that we decharge and charge the button cell with a constant current, and there are two key parameters to be monitored to see if it works well or not. There are two key parameters. The first are what you can see with the arrow, the blue arrow on the right. It is a specific capacity in milliamps per gram. We want to maximize this, make it as high as possible. And then we quantify what we call the irreversibility with the effectiveness. So what is irreversibility? It is, we want to try and see, so these sodium ions that have managed to slip into the anode, will they manage to get out of the anode? We hope that they will, but it's never 100%. So the idea is to get as close to 100% as possible and to quantify this irreversibility. To close, well, what are the results that we obtained for the Instream wood? Well, on the top left, we have the specific capacity, which must be as high as possible for the different samples, and the effectiveness. So once again, we're trying to get as close to 100% as possible for the different samples. So what are our findings? First of all, that the results are similar for all species except for the bark. So what we can conclude in terms of the process is that if it works, the big advantage is that we won't need to separate the different wood species. And also very interesting in terms of comparison with commercial materials. Here I've circled in black the typical performances of commercial materials, and you can see that Instream wood has very similar performances. Therefore, this is material that can be very competitive with commercial hard carbon. So to come back to the particular case of bark, what we confirm here is that there is a negative correlation with ash content, which is what we already seen in previous studies. So in conclusion, I come back to my original question, which is Instream wood converted by HTC. Can it be valorized as an anode in a sodium-ion battery? So I didn't explicitly put yes, but I put some different elements. So yes, it can be converted, and it does yield similar performances as commercial materials. The positive point that was identified during the study is that we didn't need to separate the species, but I did highlight the problem of the bark, but this is a point to be discussed later on. But what we also saw when we collected the wood on site is that there was a lot of the in-stream wood didn't actually have the bark. So it seemed that the bark was removed naturally during the transport, and that could be a solution. So what are the next steps in the short term? Say even in the very short term, we will be leading larger scale trials. On Monday, we'll be at the Genesee Dam with Julie and Loic to go and collect 300 kilos of wood so that we can then convert it into hard carbon for batteries. And maybe in the longer term, the bark question, and I've seen with the previous presentations, maybe we should raise the question of the relationship with the origin, transport in water, time spent in, etc., time spent in water. And it would be interesting to do comparative studies with other sources, other species, other situations, and necessarily it would be very important to carry out the economic and environmental analysis of the entire process chain to see how it could be applied. So thank you very much for having listened to me and for contributing to the work. And of course, if there are any questions, I would be delighted to answer you. So thank you, Capucine, for this presentation. Very educational and great results. So I don't know if there are any questions, whether anybody has any questions. So yes, the theme is a bit different from the others, maybe rather surprising, maybe. But yes, I realize this. But I will put maybe give you my mail in case you have any questions. Yes, but I've seen the opening on the question of the bark, which could make a link with the analysis of the origin of the wood, depending on the period or the origin of the high waters. There might be more or less decomposition, abrasion, and different materials as well. Yes, and for us, we can see this. We're going to go and collect the wood on Monday. The question is, if we can, for those where the bark has already been naturally removed, the performance is better. So the question of bark is key, really. In the chat, you had two questions from Nicolas Rabin. The first, I think you answered it, but I will just reiterate it. Instream wood have high silicium content. Does this have an impact on the production of biochar? So shall we go back to your table, maybe? Yes, I'll come back to the table. Yes, at the outset, this was something that we were really wondering about. We were thinking, oh, there's going to be a lot of silicium. But actually, I think we can see it here. Yes, there is silicium content, but the contents are really acceptable levels. If I compare this with other biomasses that we've tested, for example, grass or rice straw that can easily reach 10,000 milligrams per kilogram of silicium, and that is a problem in batteries. And there are explanations and mechanisms, of course, that we could discuss, but which mean that the performances drop sharply. Whereas here, the content is very low. And I was wondering, even if whether it was earth or whether it was just natural content, but the contents are very low. And there was another question. And of course, you know, this possible solution of iron sodiums is very exciting as compared to lithiums when we see the mining areas and the stakes around these materials. What is the lifespan, difference in lifespan between a lithium ion and sodium ion battery? Well, I might use my joker there and call upon.
Oui.
Ah, yes, I'm here. Can you hear me? Good job, Capucine. I knew Loic was there. I knew you'd be here, so I'll pass the hot potato on to him. So, hi, everybody. Loic Simonin from Grenoble. As Capucine said, I am a supervisor of the thesis of Julius, and I'm a specialist in lithium ion and sodium ion batteries. Question is with regard to the lifespan. So we're talking about cyclability. It's a number of cycles of charging and decharging that determine the lifespan of a battery. And in this case, the sodium ion is quite similar to the lithium ion. It's even a little bit better. But the big defect of sodium ion batteries currently, and this is what is an obstacle to their commercial development, is the density of energy. So we have the quantity of energy that we can store per kilogram of battery or in a certain volume. It depends whether we're talking about watt per kilo or watts per liter. And this is a little bit below lithium ion batteries. So that means in terms of the applications will be stationary, for stationary batteries where the weight doesn't really matter. But electric vehicles, it could in the future be possible, in particular for hybrid cars, but of course we cannot use it in portable electronic devices, for example, because we're not competitive enough there. I hope I've answered your question. Yes, I think you've given quite a lot of additional information there. Yeah, absolutely. Yes, Nicholas, yes, thank you very much. There's some really great presentations this morning. And that of the research on alternative batteries is really exciting. So my question was about the interest of the transfer of this type of energy. The other question was about the storage of energy. So we could imagine small size batteries, but what about bigger batteries? Because there's no limit with regard to the size in terms of production, or is there a limiting factor? I'm talking here about, for example, might imagine we would have bigger energy storage units that could be combined with other production posts. Well, on that question, Loic, maybe you should answer that, really, because it's about batteries. Yes, on the question of large-scale storage, the problem will be the cost. So we're talking about the cost per kilowatt stored. And for the time being, we're not competitive with the steps. So the cost per kilowatt is dropping fast. So lithium-ion batteries are used quite extensively now, and maybe sodium-ion batteries in the future. But for the time being, it's still too expensive for And there are other things we can envisage in the future with the development of an increasing number of electric cars.
On pourrait éventuellement imaginer
we could imagine a fleet of electric cars connected to the grid, and which would charge during the day and uncharge overnight to as a solution of storage. So yes, so we're looking at these in particular for the storage of renewable energies. So Loic and Capucine, you have a question in the chat. Can you see this? Well, once again, there are a lot of questions in one there. It's brilliant. So if I can answer, maybe, is it easy to carry out the processing processes to manufacture batteries? Do we need specific factories? Well, regarding the transformation in hydrochar, etc., there are also already demos and factories that do exist. So basically, as far as the hard carbon, but the question on batteries, maybe Loic, would you like to add something to that? Yes, regarding the transport, it's quite simple. Batteries, lithium-ion batteries are currently made only in Asia. The anodes are made from graphite, and half of it is natural graphite, and the resources are dwindling, and they're mainly produced in China. So yes, we are competitive if we manufacture the hard carbon here from the Instream wood or other sources. Yes, then there's a question on amounts of water. And so in terms of the amounts of water, that's the advantage of this carbonization. We already have part of the water there. We won't dry the Instream wood, we'll just use the water which is in it. And the water that is used in the HTC, in the process, it is recycled. We try to recycle the water to minimize the use of water. Regarding the energy side of things, yeah, we need to look at the energy results, but the interest also of HTC, we need to heat at one point, of course, but this is an exothermic reaction. So it could be of interest from an energy point of view. But of course, there is an energy cost as soon as you set up a processing. And regarding road transport, because there's a question of the road transport to move this wood towards factories that can manufacture batteries, well, not necessarily for Instream wood, but as soon as you're talking about biomass that you're going to be using in factories, there is always a question of transport. So I think because I talked about the environmental studies in the previous studies that I've seen, road transport was represented, if we're talking about carbon impacts, had a very low CO2 impact as compared to the rest. So it remained, the benefits were high.
Merci.